Hey everyone! Thank you so much for watching another episode of the Weaviate Podcast. I'm super excited to welcome Devin Petersohn from Snowflake to the Weaviate Podcast. Devin has had an amazing career in scaling Dataframes, this remarkable journey from the Marine Corps to UC Berkeley, and then co-founding Pandas with Doris Lee, and then having that be acquired by Snowflake. Such an interesting journey, and I'm so excited to be learning more about data systems for Devin. Devin, thank you so much for coming on the podcast.
Thanks, Connor. Yeah, I'm super excited to be here.
Awesome. So I really want to kick it off with this question of when you joined UC Berkeley, like what led you to the data frame scaling problem particularly?
Yeah. So I actually started my grad school career at Berkeley working on genomics and genomics problems. Um, Something that I was really interested in was like actual applications of computer science, applications of distributed systems. And so we started by looking at large amounts of DNA and trying to gain insights from those like massive consortiums of DNA. There are a lot of these things that are kind of being put together now. There's the Million Veterans Program and a bunch of other programs that are putting together your medical records with your genomic data, and analyzing these things is a real problem in big data genomics. So I was really interested in this problem. I was like, we're going to solve cancer with big data genomics, and I found some more fundamental problems actually, because as I started working with scientists, I realized that scientists value different things than software engineers do whenever they're working on problems. What they tend to value is more their own productivity, their own understanding of what the system's doing. It's less about like, does this run faster or something like that, right? You can, in fact, anecdotally, I've taken software that runs significantly faster than what people are using, and they don't, and like scientists don't necessarily care, especially in biology where you're operating in like months or weeks of studies. If you study an animal, it might take years to study the animal and to get, to like birth new animals and that kind of thing. So there just wasn't that like need for latency. But what I did notice is that they really care about, maintaining the way that they do things and maintaining their capabilities. It's all about their own productivity. And so, from there, I kind of looked at, well, data frames are kind of the same way, where we have data scientists who are operating on this, they're essentially scientists, right? They're looking at the data, they're gaining insights from data, and they also value their own productivity, their own capabilities for doing their job. So anyway, that's a long way of saying I started in like kind of one of the more physical sciences and doing some analytics on data in that world, and I kind of saw a broader problem of just data analytics in general and data science and the challenges that data scientists face when they want to scale up their work. And so, that's kind of a little bit of the journey.
Yeah, it's so cool. I really love the one line that stood out to me in your talk in the Carnegie Mellon database series with Dr. Patel and Dr. Pavlo is kind of talking about marrying data scientists and database people. And I think it's maybe some people don't appreciate that these are like two different kind of camps. One thinking about, EDA and exploring data and preparing machine learning models. The other thinking about like distributed data systems, transactions, and like, so marrying these two things. And so I really want to kind of, if we could unpack a little further about like how Pandas data frames, like what makes them so much slower than an SQL typical relational database system.
So typically data frames are used as a local copy of some database, and a lot of times the data starts in a database or some kind of flat file. CSV is also really preferred. And I think it's worth coming back to talk about CSVs later because they're human readable and that kind of thing. But there's this big difference between how people do data science and how people do like data engineering and doing these batch style jobs. And Pandas is often used interactively, and SQL is a lot harder to use interactively. Anybody who's used SQL interactively knows that you kind of write a little bit of SQL and then you test it and you look at it and you're like, okay, yeah, this looks good, and then you go and make more. And you kind of like build it up that way. Whereas data frames are a little more incremental in how you build things up. So the analogy that that I like to use is that data frames are a food court, and databases slash SQL is a Michelin star restaurant. So when you think about Michelin star restaurants, it's a very curated experience. You can't order off menu. You basically go there. You have to like dress nice, and you have to go in, and you have to. Everything's very regimented, right? Everybody gets the same experience, and it's structured so that you get that experience that they want you to have, right? It's the same with SQL. You get that experience that the engineers who built the database want you to have, and so they kind of in a way box you into what you can choose to do in SQL. And that's not necessarily a bad thing, by the way. So contrast that with data frames. If you think about data frames as a food court, well, at a food court you can just mix and match whatever you want, right? If you want to get a corn dog and you want to go and put ice cream on it, and then you can do like literally whatever you want. And there are like I have done that before. It's fun, but they serve kind of two different purposes. Where if you really need the flexibility that data frames allow you, then you should use data frames, and you should like stay in that world. SQL is all about structure and maintaining that kind of curated experience is kind of a good way to put it. So
Yeah, so I think kind of the transition question I now would like to ask is about kind of separating the API from the execution engine then. And yeah, if we could maybe unpack like how Modin sits underneath Pandas. And yeah, like I guess the way I understand it is sort of like, I've heard your lectures where you say, Pandas is single threaded, single node, and now you want to distribute it. And so that's kind of as far as I understand it, to be honest. And then like, I understand there's like all this relational algebra operators coming up with like the core primitives. Could we maybe kind of dive into that kind of stuff?
yeah, absolutely. So Modin is a system that I built while I was a PhD student. It's open source, and it's designed to basically match the Pandas API. So excuse me, if we go back to my the comments that I was making earlier about how scientists and data scientists like to kind of focus on their own productivity more than any other metric, part of that means that you kind of would also ideally want to give them the same API that they're already using, and that way and the same kind of ergonomics, because that gives them the ability to just kind of continue in their flow and not have to worry about the execution underneath. And we do this with a lot of systems, right? Like when I'm writing C, I don't think about assembly necessarily, right? When I'm writing, like there are so many different abstractions that we have in computer science, but one that I saw was missing was this kind of language layer that sits on top of data systems. And so if like Modin, a lot of people think of Modin as like a Pandas API, but that's not actually the most interesting part of it. If you ask me, like the most interesting part is the architecture and the ability to kind of target multiple APIs against multiple different execution engines. And we've done that at Snowflake. The open source Modin before Ponder joined Snowflake, it was about Ray and Dask, and Ponder had also worked on targeting the Pandas API against Snowflake and other databases. But Modin really is about kind of giving software engineering principles to data scientists, and adding some of these abstractions that we saw that were missing
Yeah.
into the kind of market. So yeah, it's more of in that sense, it's more of a compiler than it is just a system for interacting with pandas. Although most end users will look at it as like this is a pandas API for Ray or for Dask or for Snowflake or something like that.
Yeah, so that's kind of something I wanted to zoom in further on. Is you have these high level APIs in Pandas, and then you need to decompose them into APIs that are offered by Dask or Ray. And well, maybe I'll save my question about Dask for a bit. But so this kind of like API mapping is that a lot of like what comes in, like, because you described coming up with your own relational algebra intermediate representation language. Maybe if we could just like
That's
unpack
right.
further what that means. Yeah.
Right. Yeah. So as a part of my PhD studies, one of the things that helped with was designing a data frame algebra. And data frame algebra ends up being this marriage between relational algebra, like databases, and linear algebra matrices.
Yeah.
And effectively, when you bring those two together, you end up with something that's different from each, but it is also possible to go from a data frame to a matrix or from a data frame to a database. And what that means whenever we have this algebra, we also developed a data frame data model. But these kind of core, like working from first principles in this way, or these kind of core abstractions are really important to understanding how we can emulate a data frame in a database. So database might not do data frame things, but you can make it seem like it's doing data frame things in the way that you present it to the end user. And to the end user, it's no different, right? This is why these layers of abstraction can kind of really help with user expectations and user productivity. So, um, take something like order, for example. Snowflake
Yep.
on the back end is not ordered, but a data frame is ordered, right? Whenever you print the first 5 lines, you generally expect the same 5 lines to be printed every single time. That's not true of a database. If you do a, select star, you might get a different order every single time. And so what we end up doing is emulating this behavior by imposing an order on the data and kind of doing a lot of optimizations under the hood to ensure that that is being done efficiently. So how we handle things like databases and Snowflake is going to be very different than how we handle Ray or Dask. And I'll talk about Ray and Dask in the same kind of vein because we treat them both the same, right? We're not using Dask data frame or Ray data sets. What we're using is their task scheduling engine. And we actually implement an entire data frame engine on top of these task parallel engines. So we're using them as task schedulers effectively, but all the kind of algebraic operators are implemented by us effectively in Modin. And so um, in some ways, Modin can serve as like a transpiler, if that makes sense. So we just take one language and convert it to another. That would be true for like SQL, right? Because SQL is a black box. We don't really get a lot of control over, you know, the query optimization or anything like that. Um, but when we look at Ray and Dask, those are both kind of task scheduling engines, and so we do have to go in and implement all of these operators on top. So that there is a difference in how we handle these, but I think the important thing to note here is that Mona's architecture can handle both effectively, and that's why I think it's so interesting because these layers of abstraction and this algebra, the IR that you mentioned, right? Basically, it gives you the flexibility to implement these things. So
Yeah, amazing. I have so many questions about that. The whole linear algebra and relational database kind of processing. I want to come back to that, and then I'm really curious about like file formats, like the order thing, and I'm just kind of zooming in out of my personal technical interest. Like maybe for some background for Weaviate listeners, we're working on this generative feedback loop service where we have a task queue, and our task queue is just sort of simple. It distributes work to workers, and so I'm really curious about like this task engine, task parallel engine, uh, like what for query execution, like what goes into that, like what's a Ray task queue type of engine thing.
yeah. So no, it's a great question. The way we kind of use Ray in a way that lets us define a task and then define data that task needs to like operate on as a dependency. And then we also define like other types of dependencies that task might have that are not necessarily data related. They might, but they're defined at runtime. So that way it simplifies the implementation a lot if we don't have to go in and implement a separate task for each of the 600 Pandas APIs, right? The code would get really unwieldy if we had a specific task for each of those. So at runtime, we kind of can kind of pickle the function, for example, and
Hmm.
pass it to the task and have the task do some operation on that data. So um, that's generally how we use it. Now there is some coordination involved with like passing state from one worker to another and that kind of thing. That is typically pretty straightforward in Ray, actually. Ray makes that, like, defining those things pretty easy. You just basically define the output of one task as the input to a new task, and Ray handles a lot of the kind of under the hood data movement and that kind of thing for you. So, um, yeah, I mean that's generally how we're using like Ray as a, and we use Dask in the same way. I mean, it's they effectively are treated the same, are very similar by the code.
Yeah, so cool. I almost think it's like one of those like what's old becomes new again with like this whole like large language model system thing where the output of one called a language model is the input to the next, and then once you start building these systems, it ends up looking kind of like exactly like these kind of systems, and so that's why I also just am so grateful for this conversation to kind of pick into the expertise of someone who's been building these type of things. And could we go further into kind of query optimization now? Like I understand relational algebra is like if you have like three sort of set filtering operations, like one of those, set filtering might reduce the size of the set from like, let's say 10 million to like 100,000, whereas the other reduces it to a million. So it's like the order in which you do that reduces the size of the set. And is there more to it than that? Yeah.
So, surprisingly, you can get very, very far with being able to take those types of filters and do them first. That gets you a very, very far way in terms of query optimization. Um, so there are, when you're talking about a distributed system, there's there's generally a lot more that can go into this. And whenever you have a system like Modin that defines all these tasks and that kind of thing. There, it's possible to do some interesting things with these tasks. Now, Modin doesn't have the most sophisticated thing. I've thought a lot about this problem. So some of the things that I'm talking about are not in the open source. They're just sitting in my head and like things that I want to do if I ever get time. But there are certainly interesting things that you can do in terms of um, like building your task graph or your execution graph in a way that lets you bypass certain tasks altogether, or and you can do this on a finer granularity when you own the whole stack effectively. If you're just optimizing for a query, then you might say like, let's do this operator first or that operator first or something like that. So this is the difference between logical and physical planning, and the difference
Hmm.
between optimizing for the logical and physical operators. Um, so yeah, there are definitely, like, I would say, like, you can get extremely far with these filters, and doing these filters first. That's always the first thing that you do. And when you take a database class, that's always like the kind of canonical example, right? It's like you're going to do a big join, and then you're also going to filter. And so if you filter before the join, then you get, X% performance. And it's a lot of it comes down to avoiding fetching data or kind of moving data out of its cold state on disk or
Hmm.
wherever it is, and um, avoid pulling data in, and just optimizing things for the user's runtime and cost and that kind of thing. Just make these things incredibly efficient, and that involves, you know, um, being able to uh, push filters down into the storage, for example. Something Parquet allows for too. So there's a lot of, you're right. What's old is new again. It like these things come around, and yeah, I mean, query optimization is something that is very well studied at this point, and yeah, there's you just get very far with being able to push these filters down.
Yeah, so I definitely want to come back to the Parquet and file format kind of questions, but I think kind of keeping on this query optimization, I really wanted to ask about like materializing views and this whole serialization thing and distributed data systems, and particularly, yeah, as you mentioned, this kind of like data warehouse thing adds a super interesting component to it, where now you have multiple tables and even also touching on that kind of like cold cloud storage and like different types of storage for each kind of data. I guess my question, sorry, this is a pretty broad question, but just like, how does then kind of like materializing intermediate views and then thinking about like how you serialize that between the, like when you're sending it from the disk to memory, or, and then maybe it's distributed as well.
Yeah, yeah, yeah. No, this is an excellent question. Because a lot of what I think about, and a lot of the way that I've designed Modin as a system is to kind of give that snappy interactive feeling, right? And so materialized views are an important part of being able to give that snappy feel, kind of that quick interactivity. When you do the materialized views and like how you go about doing this, this is an area that you know there's been a lot of study on this in the past in database context. I think there's a lot of interesting work that can be done in the future on like the data frames and more low latency kind of interactive work. Um, there's a lot of interesting stuff that can be done there. But materialized views uh, are an important part of you know even being able to do something like present the same order to the end user when you're talking about databases um, and so yeah in Modin we have certain like cached materialized views and that kind of thing in the open source we do this a bit on the Snowflake side. When you're using Modin with Snowflake, um, you have like the guaranteed order is maintained and that kind of thing. So yeah, this is it's an important part of being able to make those things snappy, because if you have a very expensive operation and then you want to see the results of that, as you tweak things, you may not want to rerun everything from the scratch, right? You might want to kind of start at the point where it was expensive and only run that expensive operation once. So um, in the interactive setting, I do think there's work to be done here and a lot of interesting work to be done in the future. But um, yeah, you're totally right that this is kind of a very important piece of interactivity and making things snappy and especially at scale. So yeah.
Yeah, that just helped to click for me a lot. I love how in your paper you describe you have a walkthrough of an example of a data scientist who's looking through like iPhone 12 type of thing, and so that helps me understand this idea of like you've constructed this complex SQL query or like analytics query where you have some intermediate state because and then you're going to tweak it a bit and you want to reuse what you've already computed in a previous query, like how you have this iterative data science kind of workflow, which is something I want to come back to with kind of like large language models using Ponder and that kind of thing in a little bit. But further, I want to keep drilling into the technical expertise. So, so pivoting topics a bit, I'm super curious about file formats. I don't understand too much of it myself. I understand this kind of like you have sort of like column oriented storage that is optimized for like the symbolic aggregations in a particular column. And then, so I'm just kind of curious, like, what is the state of innovation? And you mentioned kind of like Parquet earlier. Maybe people listening know like you have like CSV or like HDF5 or Parquet files. I'm just kind of curious, like, what is the state of innovation around just like file formats?
Yeah, so um, a lot of people still use CSV. Parquet, of course, is a standard. There are a lot of um, you know really good options for people who want to do file formats, and a lot of the decisions generally come down to like what your company needs. So Parquet is really good if you need to push queries down. Like you only want they're good for range queries, right? So if you want to filter what you want to push that filter down to the storage, Parquet is able to do that because you just kind of read the metadata and then you decide whether you need to pull in that full file or not. CSV is good if you need your file to be human readable. that that's it's very very difficult to distribute and to parallelize reads on CSV files. They're just not. It's just not really a good standard for being able to do that. But it does have the benefit of being human readable, and that's why it's so widely used. I also see a lot of Excel, but like everybody uses Excel, so like that's partly why. Feeding Excel files into other systems though is kind of pretty common, and that's that's definitely an area where I've spent a lot of time is like parsing Excel. So in terms of like uh, you know, those I think are really common. And of course, you have like metadata stores and like attaching these metadata stores to the to your file formats and your query engine and being able to have extra power on top of the file formats themselves. But those are the kind of main file formats I would say that people are typically using, particularly with Modin and like in and Pandas in the Python ecosystem.
Yeah, and so then I wanted to ask about like one thing that I had tested out Modin is I was doing a Kaggle competition where we had one of these giant CSVs that you can just load in, and so I've been curious like how exactly do you like read a CSV faster? Is it kind of like with parallel cursors or something like that?
This is a great question, and this is actually something that I've spent like a very lot of my time on. Um, and I'll kind of try to get into the tricky parts of it because at face value you might say, okay, well I'll just read this many lines on this worker and this many lines on this worker, but it's actually not that easy, and I'll kind of explain why. So, um, reading in a CSV file in general. So generally the way that I explain this is compare the time it takes to simply read the CSV file into memory versus parsing that and interpreting the data types on each column and that kind of thing. Parsing is always going to be significantly more expensive than reading. And that opens up the opportunity for you to basically do things in parallel. And so when you think about parallelizing the parsing, um, you have to kind of choose where one worker stops and another worker begins, and ideally you do this without any communication after the fact. Um, Distributed computing is often about reducing the amount of communication between the nodes and reducing the number of times that you need to kind of do this like stop the world, everybody tell me what your results are type of thing. Like anytime you can prevent that, you generally do when you're operating in distributed systems. The reason why CSV files are tricky is because commas and new lines actually can be data as well. So if you think about Amazon reviews as like, let's say that you want to read in a CSV file of Amazon reviews. Well, review text has commas in it. Review text has new lines in it. So you can't just pick the next new line because that might end up being in the middle of your review, and then you end up with you know the wrong offsets, and your data is all messed up whenever you try to read it into a table. So then you have to think, well, I need to basically make sure that I'm at the end of a quote, because when you have this text data in your CSV file, you have to quote it. Otherwise, any CSV parser is going to have no idea whether the comma belongs to data or whether it is actually delineating different values in your column. Um, so that's where a lot of the complexity ends up being. And in Modin, what we do is in Modin, we basically need to make sure that we are not in the middle of a quote whenever we send offsets. And we send the file offsets to each worker. So um, the driver, which is coordinating all the workers, basically says to each worker, this is where you start and this is where you stop. And that's generally how we parallelize something like CSV. CSV it's a pretty difficult file form. I mean, I'm not going to be super like rough on anybody's opinions about these things. Like, if you use CSV, you shouldn't feel bad because there's obviously a reason that you're using CSV. But it is a very difficult, from a systems perspective, it's a very difficult file format to work with because file formats like Parquet are inherently set up to be read in a distributed way, right? In you have partition file support in Parquet. You do not have that in CSV unless you're chunking up your CSV into multiple files. And when you do that, that actually does help, and Modin can handle that as well. But when we're talking about a single big CSV file that you get, which is how most CSV files are honestly stored, that's when it gets tricky, and you kind of have to deal with: am I in a quote? Am I not in a quote? Where do I start reading? Where do I stop reading? And yeah, so doing that and doing that quickly, and that is taken a lot of effort basically in Modin.
Yeah, that's super fascinating. I think there is definitely kind of like related to a lot of this about how the Pandas APIs are very human friendly. I think CSV, JSON, they're very human friendly, and that's why they'll kind of continue to have value. Whereas, yeah, this escaping CSV thing sounds super difficult. So this kind of comes into a bit of the history of Weaviate as well, where we used to have this GraphQL API. I think we do still support it, but we were sending JSONs basically, and then we'd be spending a lot of time unmarshalling JSONs, and then we had a gRPC API sending like this byte stream. And I had learned about, like, I caught up on this with that data driven applications, the like Bible O'Reilly book of these data system things. And so I'm really curious about this relationship between like gRPC protocols and schemas, and then kind of like file formats, if that makes sense. Like when you say like, okay, this is this particular file format, I'm going to serialize it this way. And if there's like a lot of like interoperability or like co-design that goes into that when you have like a custom file format for like a custom kind of serialization schema.
Yeah. So in Modin, we generally for serialization and deserialization, we generally use Arrow.
Okay.
It is uh, the best the best way to send the types of data that we're dealing with. Um, Typically, when we're dealing with like serializing and deserializing file objects, we typically only send the handles and assume that like the storage is some NFS, like a network file system, or some like S3 bucket or Google Cloud Storage or something like that, where all the workers have equal access. We generally don't try to like ship parts of the file over the wire because
Mhm.
that is very expensive. Apache Arrow just plays this really important role, I think, in data movement, and um, that's why it does play a really important role in Modin and how we move data from one worker to another. But yeah, like I said, I mean the generally when we're talking about file formats, we don't want to ship parts of the file or that kind of thing to other workers. We generally recommend that people put their files in like S3 or Google Cloud Storage or some other network attached file system that all workers can access. That way you can actually do the read in parallel rather than reading in the file and transmitting pieces of that file over the wire. Because whenever you think about moving data, like that's generally the most expensive part of your workflow, right? Um, it's partially why Ray was built was to avoid that and to kind of handle iterative computation a lot better. So um, yeah, that's generally how I think about the relationship between file formats and serialization, deserialization, shipping around things. We generally try our best not to move data as much as possible, just because it's the most expensive piece of any workflow.
Oh, that's so cool. I've already learned so much in this conversation. I'm really curious about this idea of like data interoperability between Weaviate and then say like a GPU service for sending like vector indexing graphs. And I think this kind of arrow thing and this type of thinking about how you would serialize an HSW graph to maybe send it to a GPU and then use Cagra from like NVIDIA's CUVS to like build the graph and then send it back. I think that's one kind of really interesting opportunity for vector databases between of moving mass amounts of data, also maybe offloading quantization in this kind of way. I think is really interesting. And so I think kind of maybe a big question on this kind of topic, and then I want to ask further about Ponder and Lux and things like this and your kind of personal journey with that intersection. I want to ask one more technical question again about kind of the separation of compute and storage and how you think about that kind of idea.
Yeah, yeah. What's old is new again. That's the theme of a lot of these things. But um, yeah, I mean it's it's been really interesting to watch a lot of these things. Like Snowflake, for example, that's one of their core principles is the separation of compute and storage. Um, a lot of systems, Hadoop and the whole ecosystem that was built around Hadoop, and then Spark and that kind of thing. They all generally do this. Modin also to some degree separates compute and storage, where especially with Ray, where we use Ray's object store, which is separate from compute, and Ray handles a lot of the way that node to node communication happens. So or worker to worker communication, if that makes sense. So whenever we have the output of one task, we write that to Ray's object store, and then when when it's time to kind of consume that output, we read it back from the object store and operate on it. And that object store can be on disk. It can like Ray's object store is pretty flexible. But yeah, the separation of compute and storage is definitely it's not necessarily a new concept, although it it is something that I think has kind of finally caught up with the way that databases are built. And this is generally what happens in terms of like commercial databases and that kind of thing. A lot of the interesting components of other systems end up making their way back into databases, and I actually think that that's where we're headed with data frames as well, because data frames and databases are quite different. So if you think about what would a hybrid of a data frame and a database be, I think it's interesting to kind of watch over the next decade or so as databases continue to evolve, because we've had a lot of movements in the past like NoSQL and that kind of thing, but most of the like most useful pieces of these outside data movement, or excuse me, outside of the database movements, let's say, end up back in a database or a data warehouse. So, um, yeah, that's what I think would be really interesting to watch.
Awesome. Yeah, it's so interesting. This compute and storage thing is going to be super huge for Weaviate. And I don't know too much about it, but I really appreciate getting your insight on it. And yeah, just continuing to understand what this entails. So maybe one other question I kind of alluded to earlier that I really wanted to pick your brain about is about rapids and the CUDA data frames and how this fits with the Modin story and all this kind of stuff.
Yeah. So NVIDIA has invested a lot in GPU data science. They've been working on this for a very long time. And cuDF is really interesting because it's basically a data frame that lives on your GPU. And GPUs are great for certain types of computation. Um, it's a little bit more difficult to use them for some of the more wacky data framey things, but there's a lot that the GPU is actually perfectly suited to be faster than anything else running. And so the the way that we think about this with Modin is actually, we built a prototype integrating cuDF with Modin and having like this distributed GPU data frame. Um, and that proof of concept was actually pretty successful. And, it was a collaboration between, myself and some folks at Georgia Tech. And there was a lot of interesting kind of insights that we gained from that. So the way I think about it is like, we can kind of leverage these GPUs in a cluster, perhaps a Ray cluster or a DAS cluster, and we can you know basically just get the benefit of cuDF and all these GPUs, but we can also scale because we have this kind of linear scaling capability that we have with Ray and with the kind of communication algorithms that we built in Modin and the core primitives that we've worked so hard to make efficient. cuDF is actually well suited to kind of slot in there and be a part of that distributed data frame.
So cool. Yeah, I also thought it was really interesting. I think Jensen's keynote at the NVIDIA conference, he opens up with talking about rapids and how millions of data scientists are using Pandas, which listening to a few of your talks, Devin, I love like the story about Pandas and how many people love using it, and hearing about this under the hood engine internals is just super interesting. One other question I wanted to ask, kind of continuing on this Pandas story, is I remember when I first listened to Doris Lee in the MLSys Stanford seminar describing this idea of like recommending data visualizations to you. I thought it was so compelling. And this was even before large language models. Or today, I think maybe people get this idea of like you give it a CSV and you say, hey, large language model, like, produce some plots and let me know what you think. But I'm really curious about this story of how Modin and Lux, the visualization tool, like how these came together and sort of the vision and yeah, just like the whole kind of founding story.
Yeah. So Doris Lee and I go back many years, and we worked together on a couple papers. Um, so when when it came near time to graduate, you kind of have to figure out what you're going to do next. And Modin had a few 100,000 downloads and several thousand GitHub stars, and I was thinking about commercializing it. And I really wanted to you know pair Modin with another kind of killer app for interactive data science. And Modin is really heavily tailored towards interactivity and quick feedback loop and that kind of thing. It's still it's intended to feel very snappy when you're using it in your notebook. And in the same way, Lux is also trying to, help with your productivity, help with that interactivity by recommending different types of visualizations to you. And whenever I was talking with Doris, it just made sense basically. Like, and we've worked together before. We work very well together, and so the 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 and of course, we both also worked with Professor Aditya Parmeswaran. You know, he's worked with Modin since the first paper, and was instrumental in a lot of getting that paper uh, out the door, and that kind of thing. So we all three kind of came together and decided that we were going to build this startup. And so um, you know Lux, I think, has a very easy to grok um, value proposition. And the value proposition there is just like, I am sitting down at a new data set, like, what is in this data set, right? And how do you go about figuring out what's in that data set? And Doris is kind of an expert in human computer interaction and how people interact with data systems. And so it has just been, it just basically made sense, and it was great. And um, so yeah, that's kind of how we came together. We worked together for many years. She was at Berkeley, and we worked on she was on the data frame paper, and she's yeah, we knew that we would work really well together, and um, nailing down that product strategy. I mean, when we went to talk to uh, a lot of users of Pandas and of these data systems, they were really interested in getting these capabilities on their database or data warehouse. And so and Snowflake was the one that we heard the most. That's the one we built first, and then Snowflake acquired us. And so now we're kind of building out this capability, and I'm very excited about what we're building now, because I think that we have the ability to kind of build things from the ground up effectively, and kind of um, make make the Pandas API, or any other API that we build a lot more performant and snappy and that kind of thing.
Yeah, I really like the blog post series. I think Daniel Campos at Snowflake had written the first one, and I think there's like four or so of the text to SQL work that Snowflake has done, and I really love that series, and I love this kind of like database assistant type of thinking, and I think the Lux, the already thinking about how you interface this kind of like suggestive visualizations, human computer interaction, and now Modin on the back end, how you scale that, and now joining the Snowflake. I'm so excited about thinking about the future of that. And I guess maybe if I could ask this kind of like, large language models, are you like going large language models every day? How do you like, how much do you think large language models will change the trajectory of this?
Yeah, so I think largely it's very difficult to tell, like, how broad. I mean, there's no denying its impact on the industry. I think that, like, at this point, like, you'd be in denial if you were saying that large language models haven't had an effect. Now, how broad that goes is you know is anyone's guess at this point. But one thing that it has had a tremendous impact on is actually Modin's adoption specifically. And this is something I think that's worth calling out because we never expected this whenever we were building it. Um, and what I mean by Modin's adoption is basically that, since Modin mirrors the Pandas API, a recommendation for code on on the Pandas API is always going to be a lot more effective and efficient than it would be if it were on some newer API or some like lesser used API. And this is kind of like a nice benefit of having matched the Pandas API is that, well, now Modin works really, really well with GitHub Copilot. And this is something that we're still hearing from customers is that, matching the API is becoming more and more important because these large language models are so good at, I mean, part of their training data has tremendous amounts of pandas code just because there's so much out there. And so it if you're operating in something that is not quite pandas or it's close to pandas, it's still going to generally recommend maybe something like pandas or something close to pandas, and it's not going to be as accurate as something that actually is pandas. And so um, I think that large language models may end up having a bigger play in how we design APIs and systems in the future, just by the nature of them suggesting code for people, and that kind of the ergonomics that I've been talking about. The ergonomics of being able to quickly tab complete your GitHub Copilot recommendation because you're confident that like it's and you can see it right there that it is the exact API that you're looking for. Um, so yeah, I think it's an interesting space to watch. I'm by no means an expert in LLMs or anything like that, but I do think that the impact like the impact will be tremendous on how we design systems in the future and how we design interfaces. And I think like that's a great thing, honestly. I think that could be very interesting. So
Yeah, that's so cool. I hadn't heard that. I guess I kind of heard that kind of thinking before around like SQL, like some like custom SQL. Like I think Snow SQL is like a couple of operators added to SQL. So when you're trying to train a language model to learn this domain specific language, it's not like too much of a context switch. And so that's very interesting with pandas. And yeah, that whole kind of co-pilot assistant is maybe one perspective of it, and then there's also the kind of like the LLM uses Ponder as a tool to like kind of do that data analysis, and I find that to be so compelling as well. And yeah, the whole thing has been amazing. Devin, thank you so much for joining the Weaviate Podcast. Really quickly to our podcast listeners, I want to give Devin an extra thank you. I've had a fire alarm going on while we've been podcasting, so we've had to kind of pause and wait a second. So Devin, I really appreciate you for that, of course, as well as obviously more so sharing your knowledge. And I've just learned so much about data systems and all this. I'm so excited about the future of this kind of data visualization, scaling data frames, and just further understanding these systems. Devin, thank you so much.
yeah, thanks so much for having me. I had a great time.